So in this problem, we have photons are accelerated from rest by a potential difference of 4.0 kilovolts and strike a metal target. If a photon produces one photon on impact, what is the if a proton produces one photon on impact, what is the minimum wavelength of the resulting X-rays? How does your answer compare to the minimum wavelength if a 4.0 kilo electron volt electrons are used instead? And why do X-ray tubes use electrons rather than protons to produce X-rays? Okay, so this is a pretty easy question. So the first question that's asked is, if a proton produces one photon on impact, what is the minimum wavelength of the resulting X-ray? So we know, or we should know at least, that if we have E times V, that is equal to hc, where h is Planck's constant, divided by minimum lambda minimum wavelength. So we have that the potential through which the protons are accelerated, our V, is equal to 4 kilovolts. Now 4 kilovolts is the same thing as 4.0 times 10 to the third volts. 4.0 times 10 to the third volts. So we know what our V is equal to. We know what H is. H is just Planck's constant, 6.626 times 10 to the negative 34th joule seconds. That's a constant. C is the speed of light. That's also a constant. 3 times 10 to the 8th meters per second. And then we know the charge, E, elementary unit of charge, right, is 1.60 times 10 to the negative 19th coulombs. So the first part of this question, we'll call this part A. The first part of the question is rather straightforward. All we have to do is plug and chug. So let's rewrite this equation down here as lambda minimum is equal to hc over EV. And plugging in our values, plug in that for Planck's constant, speed of light, 3 times 10 to the 8th meters per second, divided by 1.6 times 10 to the negative 19th coulombs, times the voltage, which is given as 4 times 10 to the third volts. So if you plug that all into your calculator, you'll get your answer to equal 0.311 times 10 to the negative 9th meters. And you can rewrite that as 0.311 nanometers. So there we go. That is the answer to the first part. Now the second part says, so we can put a little check there. How does your answer compare to the minimum wavelength if 4.0 kilo electron volt electrons are used instead? So we're using a 4.0, let's change our color here. We're using a 4.0 kilo electron volt electron. We're using that instead. So here, for part B, we know that our kinetic energy is 4.0 kilo electron volts. Okay? And we can convert that to joules by multiplying it by 1 times 10 to the third electron volts per 1.0 kilo electron volts, right? Because we just want to get this into EV, not kilo EV. And we know that there are 1.602 times 10 to the negative 19th joules, 1.692 to the 19 joules per electron volt. So this is equal to 6.408 times 10 to the negative 16th joules. So now we just have to find our lambda minimum again, which is going to be equal to, over here, right, it was lambda minimum was hc over E times V. This time it's just hc over k, and you are going to get 0.311 nanometers again. If you plug in the constants and plug in this value for k, you're going to get the exact same answer. These are the same, and this is the same. So the final question asks, why do X-ray tubes use electrons rather than protons to produce X-rays? And the answer is because electron beams are a lot more easily produced, and the mass of an electron is so much less than a proton, so it's way easier to accelerate than it would be to accelerate a proton beam. So I hope all of this made sense. And I think that's all we have to do for this problem.